Okay, welcome back. So I like to continue to discuss this Buneman graph, Buneman tree more precisely. And again, a quick review, like the Buneman construction is like that. We have a base set, like in this example, as 1, 2, 3, 4, and then we have splits like sigma 1, sigma 2, sigma 3, sigma 4. That's basically partition this set like 1, 2, 3, 4 into two partitions. And then like the edges is basically, okay, again, like node first. The node will be just out of each of the split, we select one of the subset, and then the tuple, the corresponding tuple will be a node. So for example, like I pick sigma 1, the subset like 1 from sigma 1, and the subset 1, 2, 3 from sigma 2, and subset 1, 3, 4 from sigma 3, and subset like 1, 2, 4 from sigma 4. And then I construct this node here. And also like a node is valid only if the subset have pairwise, non-empty pairwise intersection. So if I pick two of the subsets, their intersection should not be empty. And then an edge will be just if I have two labeling nodes, I have two nodes there, and one node differ from the other node only with one split. For example, like this node and this node only differ by the split sigma 1. So therefore, like it will be connected by the edge sigma 1. And for the previous like couple videos, we show that like the Buneman construction will always give us a connected tree, or like just a connected tree. And also actually it's a redundant description. I guess tree is always connected. So and also like we also show that like any tree can be constructed using the Buneman construction procedure. So therefore, like anything we describe, the property describing the Buneman tree will can be generalized to all trees. And again, the crown jewel here, what we are interested in is like for a tree, we want to describe some kind of metric between some nodes there, and then we say like if we know the distance between f of the nodes, then potentially we can precisely specify the structure of the tree, and that's our one of the final goal basically. So we are getting closer and closer to there. And so now first of all we need to describe metric. So we will introduce this addictive tree metric. So basically remember that like because for each of these edges basically just a split sigma, right? So we can specify a somehow a distance, I guess like a distance for for each of the split. So mu sigma here for the split sigma, I have the distance mu sigma, and then the addictive tree metric. For example, like if I say like for these two nodes here, let's say I have sigma 1, sigma 2. So for these two nodes here, the distance will be simply basically like mu sigma 1 plus mu sigma 2. And looking at the example like this guy and this guy here, these two node here, the difference between these two metric will be like difference between these two distance between these two nodes here can be specified, can be quantified by mu sigma 3 mu sigma 3 plus mu sigma 4, let's say, because it's differed by sigma 3 and sigma 4. And more precisely, we can basically write down distance, let's say we use a delta notation to say a distance between these two nodes, like M1 and M2 here, will be the sum of all the mu star, so it doesn't need the star here, mu sigma, sum over all sigma here, mu sigma, and also multiplied by delta sigma M1 and 2. So I will have like delta sigma, maybe I put a star here also, delta sigma M1 and M2 will be equal to 1. Equal to 1 if that's if h sigma is between the path, maybe I write it's on the path, on the shortest path, between sigma M1 and M2, and zero otherwise, basically. And why would that happen if I have the edge? Basically, sigma is on the shortest path between M1 and M2. Note that, like, remember, like, what are the nodes? Each of the node is just a selection of the split, right? For example, like, if I have M1 here, I have M2 here. M1, I say sigma 1. Maybe M1 is S10, S2, 0. Okay, again, I will use some shorthand notation. This maybe like maybe I just have like 4 sigma here to make it simple. S3. So meaning that for this guy M1 here, I pick S10 for sigma 1, and I pick S20 for sigma 2, and so on and so forth. And I can simplify just write it as 0, 0, 0, 0. And let's say like N2 here is like 0, 1, 1, 1, let's say, right? And then apparently there's a transition from when I go from like M1 to N2, we need to go through the edge sigma 2, we need to go through the edge sigma 3, and we need to go through the edge sigma 4, something like that. And so therefore, like, it's very easy to see like what is delta sigma. Delta star sigma is basically delta star sigma is equal to 1 if actually this is actually the same if like the subset selected from sigma by M1 and M2 are different subsets. Okay, so that's basically it to the additive tree metric. And by the way, like it's often very convenient to consider like when I have a node here M1 and M2, I can compute the support of M1. Let's say the support of M1, we call that the support of M1 will be equal to support M1 is equal to S10 intersect S20 intersect S30 intersect S40 here. And let's say I have this support here include an element A, and let's say the support of N2 include an element B here. Now I can define a different metric for the elements in the base set. So I can define and have also another addictive distance measure for A and B. for basically A and B are elements of S, A, B are elements of the base sets. And I can define this as sum over sigma again, mu sigma delta sigma A and B. And here I define the delta sigma AB is equal to 1 if A how should I say, sigma separate A from B and still otherwise. What I mean by separate is like I have like this is the set, the entire set S here, and I have an A here, I have B here. So let's say if I have the sigma, like this is the sigma here, then I will have delta sigma will be equal to 1. So if I have basically this is a, let's say this is a S sigma 0, the rest this is a S sigma 1, right? And S sigma 1 include B, and S sigma 0 include A, so then a sigma can't separate A and B. So on the other hand, if I have something like this, then I will have delta sigma AB is equal to 0. Now if I define the distance between two elements this way, then it's actually quite easy to verify that I guess if I have A is in the support of M1 and B is in the support of M2, then delta star M1 M2 is exactly equal to delta AB. So because you think of that, like this is basically just sum over this mu sigma, right? So and then like whenever I have transition, basically when from M1 to M2, if I go to M1 and M2, if I need to go through the transition sigma, in the sense that M1 and M2 differ, like for the split sigma there, then of course like it also means that like if I look for an element in M1 and an element in M2, the element in M1 should be in one of the sigma, or like in S1, and the other part should be in S0, should be in the basically. So in that case, I also like I will have delta sigma AB will be equal to 1. And also like similarly, if like M1 and M2 for a particular sigma, if like M1 and M2 is the same for that sigma, for example, like for this one, for the sigma 1 here, M1 and M2 is the same, it's all, both of them belong to S1 0, then of course for element in M1 and element in M2, there will be no transition. Basically, when I say transition, it's like there would be like both elements will fall into one of the subset of the split, and so therefore like it will have like delta sigma AB is equal to 0. So therefore like it's quite easy to see that like this whole. So maybe I say that again, like if support M1 include A and support M2 include B, then basically this delta star M1 M2 is equal to delta AB here. Now I want to introduce so I have this additive tree metric here, but one thing is that it's usually more natural to just for a set here, like for a set S here. Okay, first of all, like if we look at this here, when we define like in a set A, B, and we try to define an addictive tree metric for A and B here, this kind of like is kind of like indirectly defined this for this mu sigma here. So, but for a set like starting with a set base set S, that may be like some pretty lateral distance. Basically, like I have like some lateral distance D that I know like A and B will be differed by this kind of distance, and so we'll wonder like how DAB will be related to this delta AB here, or more kind of like concretely how mu sigma will be related to this DAB here. Of course, like there can be like many ways to construct that. I guess like one of the ingenious idea for Buneman's original paper is that like he give out like a relationship like how mu sigma is supposed to related to like DAB here. So basically his idea is like the following. So if I have a whatever, like I have a set here, let's say I have a base set here, and let's say I have a sigma that of course I separate. Well, whenever I say sigma, remember that sigma is a partition of this set, so it will contain two subsets. One subset is like S0, and I have another subset. Maybe I put a 0 above, like just to keep my notation consistent, and then another subset has 1, and then so this is like my sigma is composed of this S0 and S1 here. Maybe I should, yeah, it's okay. Yeah, let me use bracket instead of curly bracket. So it's like the order of them is kind of important. Now then like I can, let's say I know some lateral distance metric between like any element in, for any element A, B in S. I know this, so I can define a lateral mu sigma here following. I can pick mu sigma as the minimum over all A, B, C, D, such that sigma separate A, B from C and D, and the value here is like D, A, C plus D, B, D minus D, A, B minus D, C, D. Usually they put 1/2 here. So let me just follow the paper. I also put 1/2 here. So that's how you can construct a mu sigma of this D here. And what's interesting is like for this lateral like mu sigma here, or maybe I'm not sure, I should put a D somewhere to indicate it's like derived from D, but actually it's okay, like it's understood here. So for this mu here, it turns out that D here will be related to this mu D, and eventually D will be exactly equal to this mu. Okay, sorry, not mu D, because it's not directly related. I need to be careful. I have this mu sigma here, but then like remember the addictive tree metric is given by this delta. Now I can put a D here to indicate that this is derived from this distance metric D here, and delta D A B again is given by now sum over all sigma mu sigma delta AB. Again, like delta AB is like delta sigma AB. So it's like whether like sigma separate A or B or not. and we'll show eventually that like under some mild condition, DAB will be equal to delta DAB, basically. So if we have some lateral metric that maybe is like can be understand from the data, and then like as long as we construct the mu sigma this way, then the addictive tree metric will be equal to the D, equal to that D there, and also like what we want to show again is that like if we give them the additive tree metric, and we kind of like specify like for all the nodes pairs, like if I take any pair of nodes and I know the additive tree metric, then the whole tree structure will be completely specified. So and so first, okay, that would be like several things we want to show. I won't show everything like today, but let's see. I probably will go up to trying to show our major result that and let me write down, that's known as the theorem in theorem 1 in the Peter Buneman's paper. Actually, like I have his paper here again. So and it's his theorem 1. So it's saying that like if I have tree and I have the additive tree metric, so here they are the same basically, then the trees will be identical, and also like this alpha sigma and beta sigma will be the same. The alpha beta and alpha sigma and beta sigma is basically the mu sigma and mu sigma that we described earlier. But yeah, that would be like a couple steps to reach there. So and before that, like I like to show a lemma first. Let's see if I miss out anything. Okay, let me show a lemma first. Let me go back to the Buneman's paper. So we will try to show this lemma 8 here. So basically saying that if we have two split, sigma 1 and sigma 2, such that like okay, I guess I in this video I didn't really kind of repeat the definition of compatible sigma, compatible splits. So I have two splits are compatible. So if I have like sigma 1 and sigma 2, they are compatible. Okay, maybe it's easier just draw it. So I will have this one will be compatible. For example, like maybe I just write like 1, 2, 3, 4 here. So this is compatible splits. So two splits are compatible. Maybe I use different color. So two splits here are compatible if a subset from the splits, we can find a subset in each of the splits such that like the splits, these two subsets do not intersect with each other. So for example, like for this, for the red one here, of course I can just pick the subset 1 here, and for the black one here I can pick the subset like 2, 4 here, right? So the complement of 1, 3, 2, 4 here, then like these two do not intersect with each other, so therefore these splits are compatible. So give another example, if I have 1, 2, 3, 4 here, so if I have something like that, then these two splits are not compatible. So because like for example, like no matter what I pick, right? So if I 1, 2, I can pick for the black one, I can pick 1, 2, I pick 3, 4, or like this yellow one, I can pick 1, 3 or 2, 4. In either case, in all cases, I will have like the selected subsets to do not have like an empty intersection. So what the lemma A said again is saying that like if I have two splits here, if I construct mu as we described earlier, if we construct mu, just like what I described earlier, we pick the laterally constructed mu there. Then this mu also have a very nice property that like as long as the mu is bigger than 0, then like sigma 1 and sigma 2 will be automatically compatible. So let's think carefully. So like this is lemma 8. We try to show this. Maybe use a new page again. So now think of like we just have the example here, right? 1, 2, 3, 4 here, let's say, or A, B, C, D. Maybe I use A, B, C, D. Use A, B, C, D. And again, like the lemma is saying that if I have mu sigma 1 is bigger than 0 and mu sigma 2 is bigger than 0, then I automatically have sigma 1 and sigma 2 are compatible. Do the proof here. So now let's just simply show that by contradiction. So first we assume that it's not compatible. Let's say if it's not compatible, remember that what does it mean by not compatible? So not compatible means that like of the sigma 1 and sigma 2, sigma 1 I pick like as 1 1 and sigma 2 I pick like let's say as 2 0. The intersection is non-empty, and also like for all the other combination it's also non-empty. Right. If not compatible, that means that therefore like it should be, as we construct, it should be something like this. Actually, like this exactly. I should have some element here such that like I can have like S11, let's say this call this S10. Actually simply I just simply sketch it. It's okay. I guess let me write it down here first. So then I can have situation like this, right? Because maybe again I use different colors, maybe better. So so I will have like situation like this way apparently. I mean like I can find element like A, B, C, D. So because like S11 and S20, let's see, S11 is this guy. S11 is this one here, right? S20 is here. So this one is non-empty. That means that this I can find an element D here, right? I can find element D here, and also the S10, S10 and S20 is non-empty. So therefore I can find element B here. And similarly, I have S11 and S21 are non-empty, so I can find element C here, so on and so forth, right? So therefore, I basically have element like this, A, B, C, D. Now then I will access A, B, C, D, satisfy something like that, and then I will have from the definition of mu sigma 1 is like minimum of like the A, B, C, D, A, B separate C, D. Okay, maybe I don't need to repeat that. So basically, maybe I put a pi here is better. And A, C pi, A pi, C pi plus D, B pi, D pi, and D, A pi, B pi, and D C pi D pi. So I'll put back to comma maybe. Right. So then, of course, that's basically for all A pi, B pi, and C pi, D pi. That's is separated by sigma, right? Sigma 1. And I look at sigma 1, sigma 1 is this guy, right? So precisely, I can pick like A, B, C, D, A pi, B pi, C pi, D pi as a B, C, D here. So therefore, this will be less than equal to 1/2 D A C plus D B D minus D A B minus D C D. And similarly, I have like mu sigma 1, mu sigma 2 is the same thing, right? I can pick like elements like B, D. Okay, I guess I don't need to write it out. Basically, I will pick elements that is separated by sigma 2, and then I basically also I have 4 terms here. I have like D. Actually, I can just write it out here. So sigma 2 here, I guess I directly write it out here. It's less than because I sigma 2 separate BD from AC, right? So therefore, I should have equation like mu sigma 2 is less than equal to AB plus CD, right? AB and CD and minus BD minus DAC. Now, if you look at these two guys here, it's exactly just opposite to one another, right? So therefore, actually, what I have is like this opposite. I mean, like this one is negative of this guy. So I have this one. I should flip the sign here. Mu minus mu sigma D is less than equal to this guy here, and of course this term is the same. Actually, the same here. So therefore, it's actually this is less than minus mu sigma 2 here. And of course, if we say like this is bigger than 0, this is bigger than 0, this is bigger than 0 here, this is bigger than 0 here, I will have a contradiction like 0 is less than 0. So therefore, like this is contradiction. So therefore, we must have the two sigmas there, the two splits there are compatible with each other. Okay, let's continue our journey with this paper by Buneman, like in the 70s. And so we will try to show this lemma line now. So this lemma line basically saying that like if we have the distance, that electric distance D, or like they call he call it this similarity coefficient, and the induced, basically the induced distance, I call it induced distance. Basically, like we have mu sigma. If we remember that basically mu sigma is constructed using this D here, and we can build delta D is basically also like a distance measure of two elements or two members in the space in the base set S there. And then we want to show that like this delta D is less than equal to D. So in other words, okay, I guess I need to erase some of this thing here. Maybe I erase this. Okay, so so we have basically what it means is that if I have like for any AB in the base set S here, so I should have something like delta D AB. Okay, my handwriting is horrible. Delta D AB that's given by sum of all the sigma, all the split sigma compatible splits there, delta sigma AB. So basically this delta sigma again like will be equal to 1 if like the split basically like separate A and B. Otherwise it will be equal to 0. So it's less than equal to DAB. So this is something we want to prove. This is the lemma. Lemma 9 there in the paper. So the proof is like that. So first of all, like we start with like consider any AB, like any AB here, and without loss of generality, I will have a path, and let's say the path like contain like M1 and 2 up to MP. So and basically M1 will include A there, and MP include B, and basically this is a path like go for each node here, M1, M2, and also on up to MP there. When I say when I say M1 include A, what I mean is like maybe I should write more clearly. It's like support of M1 include A, and this is a support of N2 include B. So that means that for all the subsets in M1, the intersection of all the subsets there, subset of S there, will be equal to support M1, and that intersection will include A. Let's see. In particular, maybe I will just write these nodes, all these nodes here. Let's say M1 as S10 as S20 and so on up to Sn0, let's say. So this is for the node. So I should write more clearly. So let's say M1, I write it as this one, right? The first node is M1. So again, I should have the support of this one will be just S10, S20, and so on up to Sn0 here. Will include A. Here, just without loss of generality, I would just assume like this is S10 is always take the first subset. Just make a notation a little bit simpler. Let's say I have S on this other end here and P here. Okay. Yeah, on the other hand, MP here, let's say I have like S11, S21, and SP1, and then SN0, something like that. This include basically the intersection of all these subsets will include B. So something like it pass through from M1 to M2. Let's say I assume there's a transition for the first split there. So I have M1 and M2. Maybe I write like this. Since this one is MP here, MP and the very end here. So I have N2 is something like S11, S20, and so on, Sn0. So it's just the first split is different. So I have this edge between M1 and M2 is sigma 1. And so on and so forth, like until like this one is a sigma p, let's say, finally connect to MP. So if I have something like that, I can find first of all, like because all these nodes are variant node, right? So their pairwise intersection has to be not empty. So let's say I have S10, of course it contains A here, so I have S10 contain A here. Now for S1 1. So S11 and S20 should be non-empty. And actually S10 wait a sec. Yes. S11 since S11 and S20 the intersection is not empty, and we assume that contain a element C1 there, and let's see, is that right? Yes, it contains a C1 there, it contains a C1 there. Let me write it this way. So it contains a C1 here, and I have like S2 yeah, actually, let's look at this S10 and S11 first. So I have S10 contain A here, right? And S11 contains C here because the intersection of S11 and S20 contains C here. And also I have B. B is not on this. It's not in S10. Right? B has to be because this contains B here at the end. B is in the S11 there, so it's in the complement S10. So basically I have B is on the other side, and B has to be contained in S11, right? Yeah, so okay, that's what I have here. So now, like, from this one here, I can use the definition of mu sigma 1. So I have the split here, like sigma 1 is like this. I have sigma, remember that this is like the definition for this construction of this sigma. So I can go back to here. The construction for this is a minimum, find A, B, C, D such that like sigma separate A, B from C, D, right? Here, like my sigma 1 here split A from C 1 and B. So I can pick A 2 times, so I have basically maybe I can skip this minimum even. So this value therefore has to be less than equal to d A B plus d A C1 and minus d A A. So this is just nothing, and minus d C1B. So I have sigma 1 like that. So now let's consider the next S20 and S21, and I have basically consider split sigma 2 there. Sigma 2, we have let's see, we have for this guy here, I have like C1 is containing S20, right? So I have a C1 here, and also like A is contained in S20, right? Because in the first node here we know that A is contained in M1, so therefore like A is contained here, and from the third node, maybe I should write one more node. I have M3 here, is S11, S21, S30, something like that, right? So from the third node, we know that like this node is a valid node, so therefore the S21 and S30 have a non-empty intersection. So we assume that S21 intersect with S30 contain a element C2. So therefore, like C2 is in S21, so I can put C2 here. And again, like B should be inside S21. So therefore, I have this one here. So you see the pattern here. So and I can continue to construct like for this is for sigma 2 and for sigma 3 I can find like SV0 and SV1 and I am here it contains C2A and here contains some C3 and B, something like that, and all the way up to the very end there we will have SP0 and SP1 there, and SP0 will contain a CP here and also like an A here and might contain B here, something like that. And let's go back to, so I have this basically have this element for each of the splits. They have these elements here, and I can write that as equation like this guy here. So for example, for the split for sigma 2, I will have mu sigma 2 is less than equal to 1/2 d AB plus d C1 C2 minus d AC1 minus d BC2. I think I made a mistake. I don't want to mix these two here. I want to mix. I have a choice here. I have a choice like A, B, and C1, C2. But I want to pick A, C2, and B, C1. So because you see, like, if I do that, like, actually that's I can have some cancellation as I add all the left hand side terms and also the right hand side terms. So let me write a couple more. Like mu sigma 3 will be less than equal to d AC3 plus d BC2 minus DAC2 and minus D BC3 and so on and so forth. And the last equation I will have like mu, I can write here, mu sigma P will be less than equal to something like 1/2 d AB plus d BCP and minus DCPA and DBB. DBB is just nothing. By the way, DA and DBB should be nothing because it is a distant measure, like so. And then, like as I said, like we can add all the left hand side and right hand side. Like if I add all the left hand sides, so I have like sum over mu sigma I from 1 to P, right? And mu's, and this basically as you can see, this is exactly will be equal to delta D AB, right? Because I have from A to B, and the transition, because this delta PAB is this guy here, right? So I'm summing over like from A to B whenever the sigma separate A and B, right? And all the sigma that separate A and B is basically this sigma 1 up to sigma P. So therefore this is exactly equal to delta D here. And the right hand side, if I add them all together, you see basically I will get lots of cancellation. So I have like this cancel with this guy here, this cancel with this one here, and then also this cancel with this one here, this one cancel with this one here, and so on and so forth. So eventually I will have everything cancel except like DAB from the last inequality and the DAB half DAB from the first inequality. So therefore, like when I add them together, it's just equal to like half DAB plus half DAB is just equal to DAB. So that gives us the proof for this equation here, for this lemma here. And this is like for lemma 9. And actually, I was thinking like to finish the theorem, but I think this video a little bit long. So maybe I will just give a couple examples here instead, I guess. So let's say, I guess I need to get an empty page here. So let's maybe I can just, yeah, it's okay. I guess I see if I already have, yeah, it's okay. I guess I will withdraw that. So let me consider, for example, I have like 1, 2, 3, 4, and let's say this is a base set here, like it's 1, 2, 3, 4, and I have like this is sigma 1, and let's say this is sigma 2 here. I use different color. This is sigma 2, and then let's say this is sigma 3 here, and then basically the tree that constructed by this actually I think I shouldn't start with this. Maybe I should just say think of like, okay, I have 1, 2, 3, 4, let's say. I shouldn't construct the sigma right away. Maybe I start with like 1, 2, 3, 4 here. Now let's say I have my D here, so this is like 4 numbers, right? I will just pick D. Let's say DAB is equal to like A minus B, just the distance there. So the difference of the absolute difference of that two values there. And then like I define the Mills mix sigma again is like 1/2 minimum of like sigma ABCD such that, okay, ABCD such that sigma separate AB from CD, and this will be like D A AC plus D BD minus D AB minus D CD. Oh, I'm writing two, but I guess it's still readable here. So it's like this one is A minus B. Yeah, okay. And then like so then what will be like mu let's say if I put this one sigma 1, let's say like what's mu sigma 1. So mu sigma 1, I basically I split between this one and the rest of this guy here. So I can pick like actually we will, of course, like that would be like a simple optimization problem. Like we may need to try all the combination, but let me just give it out. So if we substitute all the basically like for this one I have A and B can only be 1, and CD can be like 2, 3, 4. And if I pick like C and D as 2 and A and B as 1, then I will get the minimum basically, and the minimum will be just equal to 1. The difference here is 1. Let's see. Yeah, 1 plus 1 over 2, so it's just equal to 1. So mu sigma 1, if this is sigma 1, mu sigma 1 will be just equal to 1. So okay, again, hopefully I'm not confusing anyone. The split here, like I have sigma 1, maybe like I didn't Again, I guess maybe every once in a while it's good to repeat a little bit. So sigma 1 is, in this case, contain like two sets here. So I have like basically S11 or S10, S11, and S10 is just 1, and S11 is like 2, 3, 4. Okay, and let's say I can pick sigma 2. Let's say if I try this one, sigma 2 here. Sigma 2, I have mu sigma 2. Again, I the minimum value that I think like we can come up with probably is a pick let's say, I guess I have several values will give me minimum. Maybe I can pick like CD is equal to 3 and like AB equal to 2. So then I will have like basically mu sigma 1 is equal to 1. Mu sigma 2 is equal to 1. And I can also look at, so again, like if you remember, remember earlier we mentioned that we have a lemma 8, I believe, right? Lemma 8 is saying that like if I have two splits there, whenever like the mu of that sigmas, both of them are positive, then the two sigmas will be compatible. So therefore, like for here, like sigma 1 and sigma 2 are both compatible. And I can find another sigma. So if I 1, 2, 3, 4 here, I can have a sigma like this. So I will have like sigma 3 like this. And you can easily verify like mu sigma 3 is equal to 1 as well. And I want to say that like this one, for example, like if I pick, let's see whether this one is I think this one may be okay. Maybe I should pick this one. So if I say this one is sigma 4, I believe this one should not be compatible with the other. So for example, like let's see, sigma 4, I can pick maybe like mu sigma 4. Actually, I can just pick some A, B, C, D here. Maybe I can pick like apparently is less than equal to DAC plus DBD minus DAB minus DCD. And if I pick like A equal to like let's say 2 and B equal to 3, C equal to 1 and D equal to 4. Let's see what happened. Then this I get 1 here, I get 1 here, AB I get 1 here, and CD I get 3 here. So this actually give me -2. So it's already like less than, okay, and this probably not, I'm not sure it will be the minimum values I can reach, but I can be certain that mu sigma 4 is negative. So since mu sigma 4 is negative, like it won't be compatible with like the other sigmas. So therefore, like this sigma 4 is not valid. So I have this 3 sigma is valid. And remember that like we have an example earlier. This is basically will give us a path graph. So it's basically what I have is just a sigma something like again, let me use a shorthand notation. I will say 0, 0, 0. So meaning that like for the first split I pick the 0 set, and the second split I pick the 0 set. Also the first split I pick the 0 set, and connect with the last one as sigma 1, and the second one is like 1, 0, 0, right? And connect with like sigma 2, I have like 1, 1, 0. Basically the first split I pick the set as 1, 1, and the second split I pick the set as 2, 1, and so on and so forth. So this connect to similarity as like 1, 1, 1. So this corresponds to a tree, like basically just a path graph like this. So let me give one more example. So I need to maybe I erased. Yeah, maybe I erase this one. So let's say I have a similar one. I have 1, 2, 3, 4 here, and now I consider let's say this as my, let's say maybe I consider this one first, this as my similar one. Let's say this as my similar one. So and maybe let me sketch the everything first. Like let's consider this as my similar one, and this as my similar 2, and this as my similar 3. I think like we have a tree similar to this like before, but again let me use this distance. Assume again that dAb is just equal to the absolute value of a minus b here. Then let's look at like sigma 1 is equal to the mu sigma 1 is the mean of, again like that basically maybe I can just actually mu sigma 1 is actually equal to 1. Is we can verify that. Basically pick A, B as 3 and then C, D as 4. Let's say this should give me like mu sigma 1 is equal to 1. And let's see, for sigma 2, mu sigma 2, yeah, actually all of them should be equal to 1. So I should have like mu sigma 2 is equal to 1 as well, and mu sigma 3 is equal to 1 as well. And again, like, all 3 of them is like bigger than 0. So therefore, like this splits are all compatible with one another. So, and actually, if we want to compute the, actually I forgot to give example to compute the delta there. So given this mu here, like I can compute the delta. Actually, this corresponds to a graph, right? So maybe let me draw. Okay, I need more space though. So I guess maybe it's okay. Let me have 1, 2, 3, 4 here. So if I swap the sigma 1, I have sigma 1 swapped by this guy, and then this one, and then this one. So this will be connected by sigma 1 here. And then let's see, I can swap maybe I can swap the sigma 2 here. So if I swap sigma 2, I will have 1, 2, 3, 4. I have like this, and then like this, and like this, right? And I will, these two nodes will be connected by sigma 2. And then finally I have another node. Basically I try to flip the sigma 3, so have the complement basically S1 S31 instead. So like 1, 2, 3, 4, and like this one, and this one, and these two nodes will be connected by sigma 3. And then now I can compute, for example, like what's the distance between these two nodes. So let's say distance between these two nodes. So then will be like equal to mu sigma 3 plus mu sigma 2, right? And by the way, like this is or like actually I can compute the delta from this one and this one is basically the delta between 2 and 4. So because for this one, this node can also be represented by the support of this node here. The support of this node is like the intersection of all the subset that will have 2 here, so this therefore have a 2 here. And for this guy, the intersection with this is 4 here, so I have 4 here. So the distance between, like, maybe I write delta d 2, 4 here will be just equal to mu sigma 3 plus mu sigma 2, so therefore like it's equal to 2 here. And I can similarly do, for example, like from this guy to this guy, like the delta d 3 and 4 is equal to like mu sigma 1 plus mu sigma 2, and it's 2. So it's pretty intuitive. So it's just a simple numerical example, and I guess the next time we'll really complete the proof of Theorem 1. So basically it's trying to show that if I'm given with the addictive tree metric, so Theorem 1 is here. So if I'm given I have 2 trees, let's say if I have 2 trees, and if the addictive tree matrix is the same, so basically if I look at like between 2 nodes, and always like the tree metric is the same, then the trees will be the same. And so okay, like we will come back to that like next time.